Welcome to class. In this video, we're going to take a look at solving non-homogeneous systems and what tools we already have to do those with. Well, the game plan from here is to just use all the hard work we've done so far in this class. Because we have all the same results on systems of differential equations, I still have a principle of superposition, and I still know the general solution can be decomposed into a complementary and particular solution. And those two solutions mean the same thing in this context. A complementary solution is the one we obtain by solving the homogeneous system. If you haven't checked out those videos, please go do so now. The particular solution, however, we've already seen a lot of tricks for how to find. We just need to talk about how to do them on systems instead of on individual equations, namely undetermined coefficients and variation of parameters. But before we get there, let's first talk about the complementary solution, because we haven't seen a non-homogeneous system yet. But here's one for you. Do you notice I have functions of the independent variable floating around at the end? So now I can't write this as u prime equals au, but I can write it as, if u is my vector of my dependent variables, I can write this as u prime equals 1, 3, 3, 1 u plus negative 2 t squared t plus 5. And here, a common notation would be to call this guy A and this guy F. Now, the complementary equation is exactly what you might expect. The complementary solution is the solution to the complementary equation, u prime equals a u. Drop all the stuff at the end, what do you get? We know how to solve these guys. First step is to get eigenvalues. Turns out, lambda 1 is 4, and lambda 2 is negative 2. Next step is to get their corresponding eigenvectors. Turns out there that v1 is 1, 1, and v2 is negative 1, 1. Great. Where do we go from here? Well, now I know the complementary solution, since those are two distinct real eigenvalues, is going to be c1 times e to the 4t, 1, 1, plus c2 e to the negative 2t, negative 1, 1. Great. Complementary solution over. How do I get the particular solution? So to summarize, we found the complementary solution to be this guy. And now we need to find a particular solution. Well, we can use any of the tools in our tool belt from before, including undetermined coefficients, or annihilators, or variation of parameters. But I want to zoom in and show at least undetermined coefficients and variation of parameters quickly in this video. I'm going to skip over some of the details in between, but I want to show you how to adapt this to higher dimensions. I would recommend using undetermined coefficients if you'd rather do more algebra and less calculus. The idea is the same, that my complementary solution shows exponentials, but my function over here, my forcing function or my reaction term or whatever you want to call this right-hand side, this guy looks like a degree 2 polynomial. So I would expect to actually have a degree 2 polynomial. Right, so maybe we try a solution of the form of a quadratic, except that this time I've actually got two quadratics at the same time. And just like we did before, I would plug this guy into the differential equation. In order to do that, I need its derivative. I get 2 a1, a2 t plus b1, b2. If it helps you to write these all in scalar form first and then go back and assemble it into matrix form, you can do that, by the way. And now I'm going to throw everything into the equation. Just a sec. And here it is. here is up prime equals a times up, are these three terms, plus splitting everything up in terms of degrees of t, that's the other piece here, my f function. So, just like before, I want to match coefficients on either side. I know that the constant terms should be the same on both sides if this is a solution. I know that the linear terms should be the same on both sides if it's a solution. And I know that the quadratic terms on both sides should be the same if it's a solution. And I'm going to look at them from degree 2 down. Catch you in a second. All right, if I look at those quadratic terms, it gives me a system of two equations with two unknowns. I can solve to get a1 and a2. Now that I know those, I plug those in everywhere else. I look at the linear terms, I have a system of two equations, and now two unknowns. I solve to get b1 and b2, plug them in everywhere. Now when I look at the constant terms, I have a system of two equations and two unknowns. Quick typo there, corrected it. Now I know the particular solution is negative 1/4 3/4 t squared plus 1/4 negative 1/4 t plus negative 2 3/4. And adding the particular solution to the complementary solution would give me the general solution.